From the trenches of World War II to the hospitals of today, antibiotics changed the world. But now, they're losing their power. Today, I'm joined by an expert researcher to unpack how antibiotic resistance could become the next major health crisis. This is more than a sore throat, it's a global emergency. And yes, finishing your antibiotic cycle really does matter. Let's hop in.
Thanks, Ella. Thanks for the invitation, and hi to the listeners of DeSci Podcast. My name is Chandradhish Ghosh. You can call me CD. Generally, everyone calls me CD, so let's go by CD for the time being. And I'm a researcher. I have been researching antibiotics since 2011, and I am involved in many projects, starting from how antibiotics are designed and how we can go to the next generation of antibiotics. And also, I'm in the process of founding a company for antifungals, which we will also talk about.
Amazing. Thank you so much. To really set the scene, I think we can sort of cast our mind back, 100 or so years ago, where you could fall and scrape your knee in a dirty road or a pond or a bog or wherever you're going to be living. And that could be a death sentence for you. You could get an infection, it could move into your bloodstream, and it could be the end of your life. And this was pretty fundamentally changed by a man named Alexander Fleming,
That's
who, was the sort of inventor of the first antibiotic. And it's a really interesting story, how it happened. I think it's a really good example of like this classic scientific method of, a scientist noticing a change and really pursuing it further. I'd love you to tell me this origin story of antibiotics.
That's great. So I'm glad that you brought it up. It's actually something that all scientists actually do. So Alexander Fleming was working on a deadly bacteria called Staphylococcus aureus, and he went for a holiday, leaving some colonies out on a petri dish. This is bread and butter for most biologists or microbiologists, let's call it this way. And there was a contamination but by a fungal strain, and he saw that around where the fungal strain grew, there was no bacteria. And then he realized that the fungi were, which was called Penicillium notatum, they were producing some antibacterial compounds. And I must tell you that it's actually, he is not the first person to observe it. There were other people behind who had observed it.
Wow.
There was a doctoral thesis student, I'm forgetting the name, but there were several other people who observed something like this. And one of these guys actually went to their cow sheds and saw like a lot of the farmers and the people who were with the cattle, they were using something like that to treat the cattle so people had observed it. It was Fleming who actually went about and did something about it. And it was quiet for 10 years or so until somebody else took it up.
It's so interesting for me and how often it actually crops up in history that communities of people will have long used these sort of scientific, discoveries way before we understand why and how they come to be. For example, these farmers and their cows. So after Fleming and co. had sort of observed these changes, how did the world change once antibiotics started being developed?
It's very good. It's a very good point that you bring up. So Alexander Fleming made this discovery in 1928, and for the next 9 years or so, 9 to 10 years, nothing really moved until some other people noted the paper, and then they realized, well, they need to isolate this compound in bulk amounts. And there were a couple of researchers at Oxford University, Flory and Chain. They realized that they need to scale it up and produce it in quantities that they can actually test in a clinical setting. So they managed to make it in larger amounts and isolate the compound penicillin in larger amounts, and they treated 8 mice with it. 4 of them were left untreated and they died, and 4 of them were given penicillin, and they survived. And then they realized that they were in the brink of history of making an antibiotic that you can treat infections. And they could not do it in the UK, and then they had to move to the US. and worked with another company. I'm forgetting where it's based, but somewhere in the US, and they scaled it up in larger scale, so that the soldiers who were fighting in World War at that particular point of time needed antibiotics, and they would be given this dose. So they really scaled it up for that reason. And so the Allied forces actually had enough penicillin, and that saved numerous lives, as you can make out. And you can see before antibiotics were discovered, the lifespan of an average human compared to the lifespans that we are having now there's a distance of around 30 to 40 years, and because of antibiotics.
Wow. Wow. Yeah, pretty fundamentally has reshaped human survival. I think it's also really interesting the point about sort of this. So you said 1928. So we actually are almost at the 100-year anniversary of antibiotics, which is quite amazing. But the sort of difference between sort of World War One, where there were so many deaths that were related to like infection and stuff, and especially I guess with trench warfare, so many young soldiers being sort of taken down by infections, and then how by World War II there was this resource. And I think, I mean, I might be incorrect in this, but I think also canning techniques also came around, sort of also around a war. It's interesting sort of when there's large swathes of money and emergency, how fast things can be scaled up. I mean, the COVID crisis is an excellent example of this.
Very good example. And the years that followed actually was the golden years of antibiotic discovery. In the 50s, so there was Selman Waxman who came up with, I think, streptomycin. He and his PhD student, who apparently had a pretty difficult time in the lab, but they developed another class of antibiotics. And long after that, like till 50s, 60s, 70s, we had a steady flow of antibiotics. And in the last 30 years, however, it has dried out. Like we don't have, there was a 30-year pause, and now there are a couple of molecules which are really making the waves, that can be antibiotics with a different class of action. So it's very important to understand that antibiotics, the moment you start using it, bacteria, if you do not use it for the required amount of time, bacteria start developing resistance to it, and so they become obsolete. And so you need to have a steady flow of antibiotics. And only very recently there is some new class of antibiotics which might make it into the clinics.
Interesting. What would you diagnose this 30-year gap sort of cause? Was it just a lack of interest from pharma and biotech, or was it that it just became a lot harder to discover antibiotics?
It's a very interesting point, and it sort of goes into the commercial potential of antibiotics, as well as the other things. Like, look, if you're a business, you would want the amount of money that you invest into something to be doubled or tripled, or like at least there has to be a profit margin, right? And so I'm quoting numbers. When I was a student, I read this number somewhere. These are obsolete, but still I will. So it takes 15 years and $15 million to make an antibiotic, right? And so you now start using it in the clinics, and then the bacteria start developing resistance against it, so it becomes obsolete. So the molecule that you spend 15 years, it's there for 3 years in the clinics, and suddenly, well, it's not very active anymore,
Yeah.
And so all the money that you put in suddenly has to be, put into another new antibiotic. So this model, is not working very well. If you compare to, let's say, a diabetic drug, an anti-diabetic drug. So that means that, you need it for life. So for the profit margins for the companies who are going to use it, it's a steady flow of money, right? And for antibiotics, it might get obsolete. So this is failing, as you can see. So back in the 50s, 60s, where you were really researching and trying out to come up with new antibiotics, and they were active for a long time, but then there were cases of resistance, and then you had to come up with a new one. And so people have been doing it for years. There are many molecules in the pipeline. However, the FDAs and the other approval agencies are also pretty strict, and there are good reasons to be strict about it. And so the profit margin decreases for a company which invests into it. That's why the current model is failing, and we need to really find an alternative model.
Yeah. I mean, you're definitely preaching to the converted here on the DeSci Podcast. And that, healthcare and drug discovery shouldn't necessarily be guided by profit margins. It should be guided by what's going to be the most essential in healthcare. It's a bit of a scary fact, I think, that we're on this sort of, it feels like a continual sort of escalator of sort of having to reinvent the wheel so many times. Can you please describe what is sort of the cause of antibiotic resistance? How does it happen?
So to tell you about it, I have to tell you a little bit about the mechanisms of action of an antibiotic. I will try to simplify it because I know the audience is pretty broad. So let's look at it this way. So like inside a bacteria is if you go inside the bacteria, you'll find there are a lot of different biochemical and biophysical or a lot of biological processes. So what an antibiotic does is it stops one of these processes, right? And it's equivalent to sort of entering a house. Let's say like you enter a house and you change something in your kitchen or of an unknown person, let's say not even your own, but unknown person's kitchen. And then it's not functional anymore, right? You take away the oven, for example, and then the people cannot cook anymore. And so the whole thing falls apart. So an antibiotic is something like it'll go in, it'll stop an essential process within a bacteria, right? Now, if I'm smart, I will probably lock my oven in a way or tie it to a post. So bacteria develop mechanisms where the processes that the antibiotics were targeting, they find a way around it. As a result, that same mechanism for which the chemical compound was acting before will not work anymore, right? And so if you do not complete a course of antibiotic, then there is some residual amount of that compound remaining in your body, and the bacteria feed on it, and then they understand that, oh, it's starting to work on this process of ours, and we'll work around it. And with prolonged exposure, that's what it does. One of them find a way to work around it, and then it transfers it to the other, and they grow, and those are the ones which survive in the end. Does that make it slightly better?
Yeah, no, that's super clear. Thank you. I think also I remember, throwing myself back to my university biochemistry classes as well. One of the other things that really stood out to me is that obviously bacteria have much shorter life cycles. And so this ability to develop and sort of evolve to essentially, I mean, they're just evolving to protect themselves from a risk. But their short sort of life cycles mean that they can iterate quite quickly. And what would be 3 years for us, as you were saying, of an antibiotic is, out there for 3 years, is many, many iterations of them sort of improving and protecting themselves.
So imagine like every patient is infected by some bacteria, right? And so each and every patient is receiving an antibiotic. So if you just do the math, then you can understand that in each of those patients, there is a possibility that one bacteria in that system would be able to develop resistance against it. And once it does, somehow, if it can spread from that particular patient to somebody else, and then, well, the bacteria is there. It's exactly like COVID in a way, right? It will spread. And this is what happens.
Yes. So interesting. I mean, it's very interesting because it also brings me back to a conversation I once had that kind of really shifted my understanding in that sort of a virus or a bacteria, when it sort of colonizes a host, if it's very quick to kill its host, it actually limits its own opportunity to propagate and spread. And so where we would say like a very deadly virus like Ebola or, COVID in the beginning was I think you classify it in your head as like, that's a really amazing sort of bacteria that can cause, or virus that can cause this sort of damage. But actually it's a very bad, categorically bad bacteria or virus, because it's not allowing itself to propagate. There's also this interesting sort of balance where it kind of just likes to keep the host alive, and sort of it's like a lot of give and take about how it exists in the body.
That's true. I mean, I have to say that viruses act slightly different from bacteria. I mean, there are millions of bacteria, billions and trillions of bacteria already within your body, within my body, and especially in the gut. So and they are essential for our survival. In fact, a rule of thumb is around 10 times more of bacterial cells in your body than your own cells. That's and people are challenging that number. Now they're saying that's even more. And so you can understand that all of those bacteria are very important for you being healthy, And so that's the whole new area of research of the gut microbiome and all the impact it has. So it's also important to remember not all bacteria is bad for you. And in fact, some of them are essential to have in your body. So repeated use of antibiotics might kill the good bacteria, and you don't want to do that.
Yes.
And that brings me to the next point of like, we have to find a way of killing bacteria, or only one bacteria, and spare the others. Like kill the rogue one and spare the good ones, And that's a part of the research that I'm currently doing as well, on something called antisense oligonucleotides to make them antibacterial.
Interesting, to target the right thing. Yeah. I mean, I think maybe this is a sort of a good time to sort of kind of touch on the story of like the average person take an antibiotic. And I know from like my personal experience, you get sick, you start to realize that, your orange juice and sort of tea aren't going to kick it. So you go to your doctor, you go to your GP, and they'll prescribe you antibiotics, which generally they'll prescribe you a cycle, and then you'll be 2 days into your cycle and you'll feel better. And then you can, I think, me, not so much. I promise I am a very astute antibiotic taker. But I think most people sort of feel like, okay, cool, antibiotics actually kind of make me feel a bit shit. And, I also know that they're wreaking havoc on my gut microbiome, because also, there's so much wellness information out there about, your gut microbiome and all this sort of stuff. And they feel inclined, like, or they just go, I might as well just not take the last 2 days. And then sort of also in parallel to that, your GP will often say, take a probiotic as well. And you'll go to your local pharmacy, buy a probiotic. Generally, also what I learned as well, which was terrible, is that most of the sort of over-the-counter cheaper probiotics have a very limited sort of bacteria variety. And also in the freeze-drying process, most of them can't reanimate. So sort of the payoff of what you're actually getting once you take them is so low. So I think it's like it just seems like the perfect storm of like creating and building this bacterial resistance, and also not having adequate probiotics that people are taking that are really going to start to influence your general health. And then what happens? You get sick again, and you take antibiotics again.
It's a bad cycle. It's a vicious cycle. And I think as we learn more about the gut microbiome, a lot of these changes will come in place. And, like what sort of probiotics you should take, what's something that's lying in your fridge. For example, yogurt is lying in your fridge, and it's an essential pool of probiotics. And there are many others. And thankfully, even a lot of influencers on Instagram and all the other social media platforms are aware of it, and some of the information that they are providing is actually very, very scientific and very good about what kind of at-home remedies you should take to take care of this problem. But I'm very glad that you brought it up, and you also realize the importance of it. I mean, the more we talk about it, the more people will get to know, the more they'll be able to take care of themselves,
Exactly. And I think also like in this sort of story of going to visit your GP, and as a scientific communicator, I'm very passionate about like explaining to people why something is the way it is, Because I think once that people understand that not taking your antibiotics is going to lead to quite a disastrous situation for not only you, but for the rest of the world. Because, you go and share a fork with someone or, cough somewhere, and then all of a sudden you've passed on your drug-resistant bacteria to someone else. And it's really essential that people understand why. And then I think sort of they're much more inclined to just stick it through. And generally, antibiotic cycles, they're 5-10 days. It's not your whole life. You can stick it through.
Exactly. And like I have members in my own family who have tried to tell many times that, please complete your course, listen to the doctor. But, they start feeling better after 2-3 days because the antibiotic is working.
Yeah.
And they feel like, oh, it's fine, I'm fine. And so I don't need it anymore. And this is where you make the fundamental mistake, like if you do not complete it, there would be some of those bacteria which have had a little dose of the antibiotic and have a way to work around it. And as a result, yes, you should be responsible not only towards yourself, but also for the community around you. And unfortunately, I think we scientists do not talk enough about it, or we are not great communicators so that everyone gets to know the importance of it.
Yeah. Well, thank you for getting on the podcast and helping educate our audience. I think maybe one of the more critical questions as well is as someone with such deep domain expertise in antibiotics, when do you decide to go on antibiotics? What's the line that you draw?
So I have a very simple rule. I just follow the doctor because, I'm a scientist. I understand how things work, how to design new antibiotics. But, I'm not a trained physician. And so I have to rely on the doctor's expertise. So if they tell me that I should do it, I do it. I don't question it because it makes me clear in my head, So I tell the doctor, of course, that, I'm an antibiotic scientist. I develop new antibiotics, and the person decides because, they have had so many cases, so many people to deal with. They know they will probably do the right job. And I don't self-prescribe at all. And I just follow the instructions. I think that's the right way to be. Because they are the right people to know, and they're aware of antimicrobial resistance. They're aware of all the problems, and even then they decide that you need it. Probably you need it, and so for me it's very clear. I just follow them.
Okay. I think that's very clear advice. Okay, so I feel like we've somewhat painted a bit of a scary picture in sort of this rise of drug-resistant bacteria. Very poor over-the-counter probiotics, and a sort of lack of interest maybe, or maybe not a lack of interest, but a lack of profitability in antibiotics for the greater pharma industry. So could you maybe talk me through what is the next sort of 10, 15, 20 years landscape of antibiotics looking like? Are there, antibiotics being developed? I'm sure there are, but is it a concern that we might sort of really run down the list of antibiotics in the next 100 years?
Oh, okay. So number one, there is light at the end of the tunnel. So
Thank you.
thankfully, there are quite a few antibiotics in the clinical pipeline. And I think that some of the big industries, some big companies like Roche is heavily invested into it. GSK is heavily invested into it. In fact, one of Roche's compounds, Zosurabalpin, I think, it's undergoing clinical trials right now for Acinetobacter baumannii. Is a special bacteria, and for treatment towards that. It's a new class of molecule. So I believe that the big pharma can take the risk, but the small ones or a startup, it's very difficult for them. However, if you go back the academic route of things, like where the citizens are paying taxes and that funds academic research, and antibiotic resistance is a great thing to study. not only, you can study a lot of different things associated with antimicrobial resistance. And one part of it is to understand all the different processes that bacteria start using to develop resistance. And the other one is to counteract them. And that is to develop new chemistry, new ways of counteracting them. And I hope that in the coming 10 to 15 years, the pharma, the big pharma, as well as academicians, they get onto the same page. The big pharma realizes, okay, we need to help these people. The academic researchers are actually trying to make the next drug. It's just that sometimes they lack funding, and they need to have one or two projects where it's not for profit, but to take them forward. And also there is a great new thing which is open source drug discovery, which also might fuel this particular field, propel it forward quite a bit. So I'm hopeful, and decentralized science, I hope, will also make a change in this particular direction. And one of the reasons I am here talking to you is I believe that if profit making can be taken away from everything, then a lot of the other important problems can be solved. There are many diseases which are affecting not parts of Europe or parts of the US or the Western world, but in South America, in India, in Africa, where already they're resource poor. For example, leishmaniasis is another problem. There are many of these parasitic diseases which do not have any funding, And so it's less likely even for academic labs to pursue it, because who's going to fund it? And these are important problems. 30,000, 40,000 people are dying due to leishmaniasis, something that if there are more people who are studying as much, people study cancer or other diseases, then, we'll have some way forward in that direction as well. So, but I'm hopeful for antibiotics with the three models that I said: academia industry partnership, open source drug discovery, and maybe decentralized science or something like that.
It brings up an interesting thought for me. So I myself am South African, and I studied my biochemistry degree at the University of Cape Town. And I now live here in Germany, with Molecule. And it's been really interesting speaking to scientists that are coming from the US or Europe, because I realized how fundamentally different a lot of my education was at an African university. So, we did deep studies into leishmaniasis, HIV, tuberculosis. A lot of what we studied was around these infectious diseases, because they are the most prevalent sort of diseases within our nation and greater sort of continent. But it's really interesting. There's so little funding there. And then sort of chatting to scientists from European institutions, and it was a lot more, you have this sort of luxury to study like anti-aging and maybe even cancer, which is like obviously essential, but also is not within the boundaries of sort of an infectious disease that can really rapidly, spread through populations. But then sort of there's also this, where's the money? And it tends to be in Europe and in the US. So that's one of my hopes as well, deeply, deeply, for decentralized science. There's a little bit more sort of equitable distribution of funding, because I think, to maybe like counter your point a little bit, I do think people are out there studying it. It's just about how much they're able to progress it, because I think, the jump out of, studying it and working on it within a university context to like operationalizing it or, getting it commercialized, huge.
For sure. Because you brought up cancer, I'll bring up a point which I think is very close to my heart. Is a lot of people who are suffering from cancer actually do not die due to cancer. They die due to infectious diseases. They die to fungal infections. They die to bacterial infections. So just because you're thinking that, I'm making an anti-cancer drug, well, it might be a cure for cancer. However, your body is already, obliterated, and, the immune system is not functioning anymore because of the progression of the cancer. And if your immune system is not functioning properly, it becomes a source for all the fungal infections to set in, all the bacterial infections to set in. So secondary infections, even when you're plagued by another disease, you might die due to an infectious disease in the end. And so people always often overlook this particular point of thought, that you should also take care of the other infections. And for that, even if you're putting some money towards cancer, which is extremely important, there's no question about it. However, a lot of those people will also suffer from a secondary infection, and they need to be taken care of as well. And so it's a how would I say, double-edged sword. You need to take care of both the things. And you raised the point about how some parts of the world are privileged to not to deal with so many of infections and everything, and there's not so much of funding. And it's funny for me, but when I first came to Europe 8 years ago and I started working here, even in my department, which is one of the great departments in the world, I found a lot of people did not know of leishmaniasis. A lot of people have not heard of some of the diseases that I have heard some of my family members or friends would suffer from. They've never heard it. And so the geographical location of the disease, of course, is directly proportional to the amount of funding that it receives. And unfortunately, this is a sad truth. And the more you work on it, the more you talk about it, I think some amount of funds will be diverted towards. Even if one person thinks that, okay, my next set of investments would be towards helping some people, if there is money to be made in the process, great. And if one person thinks like this, I'm happy that we are doing this podcast.
Yeah. I think that the fact about secondary infections, I had never considered it, and it's so true. Especially because I think, cancer drugs tend to be quite ravaging on the body. And the moment your immune system's down, you're open. And especially, I think we've also seen a rise of superbugs, which tend to sort of also, where do they occur? Often in hospitals. Where are people getting cancer treatments? Often in hospitals. Could you maybe talk about what a superbug is?
So superbug traditionally is one of those drug-resistant bacteria that we talked about. So some of them have developed resistance against many different antibiotics, and so let's say we have 10 different drugs and it's developed resistance against 9 of them. So that's a scary situation, right? So that means all of the drugs that we have at our disposal will not work if against that particular bacteria. And so that's how it's actually a colloquial term. So you would not hear it in the scientific community. But it's an important word because it's caught on in general public, and superbug is basically a multi-drug resistant bacteria.
It does have a good ring to it. So
For sure.
maybe it's just easy to say, I'm in the business of marketing science, so I can spot a good word when I see it. Okay, I think, that's all very, very interesting. I think maybe we can move a little bit into what you're working on at the moment. So I know we've just, spent the first 30 minutes speaking all about antibiotics, but I believe you're currently actually working on antifungals. So could you please talk to me about this journey and this transition?
Very good that you bring it up. So I must say that, what puts food on the table is my research on, antimicrobial resistance still. So I'm trying to develop antisense oligomers at the Helmholtz Institute in Würzburg to try to target bacterial mRNA. That's what puts food on the table. But there was a project that I started when I first came to Germany at the Max Planck Institute of Colloids and Interfaces in Potsdam, where I started working on antifungals and leishmanial drugs. And so throughout my life, I've always been towards infection and how to, find ways to, take care of infections or develop new strategies. So for me, there are two strategies, which is clear. One is you make the existing drugs better, or you work towards a new innovative therapy. So what I'm currently doing at the moment, which on a daily basis, is try to find a new way of making a new antibiotic. What I started back in the past, which I'm trying to also spin out of Max Planck, we have is how to make an existing drug better, and that's Amphotericin B, which is a great drug. It's an antifungal drug, but it's got huge problems of toxicity. So people who require it actually might also die from the toxic side effects of this particular drug. And in the drug industry, for anything that you can take orally, like take it as a pill, it needs to be water soluble. And unfortunately, amphotericin B is not water soluble. And so what I did was I made a new formulation of it, and that formulation makes it water soluble, and it becomes less toxic. And there are some formulations available in the market which take care of the toxicity part as well, but they're extremely expensive. And the formulation that I made, keeping all those people in Africa, in India, in South America, that they can have an affordable, treatment. So that's water soluble, that is less toxic and more affordable than what's available in the market. And this is what Olexia Therapeutics, my startup, which I'm trying to spin out of Max Planck, is trying to develop. And to be honest, although this is only with amphotericin B, but my research has shown that you can use this formulation for other drugs as well. You can make them water soluble and less toxic. And so it's a broad thing, but my best compound is this amphotericin B formulation. It's the most advanced one.
Amazing. I'm grateful that you are out there doing that work. To understand, also really about why creating a water-soluble drug is so important. There's a really interesting tie-in, with science and sort of human behavior, which I harp on this point a lot, sort of about this sort of silos between different research areas. But you can create a great drug, but if it's not very easy to take, if it's not easy to transport, it's not easy to scale up the production, people really struggle to take it, and then it's actually not such a great solution. I actually was chatting with a previous podcast guest about this very topic, sort of about how in sort of discovering and developing the drug is only really the first step of how much it's going to help people, and that there are a lot of sort of environmental factors, such as needing to take an injection versus being able to take a pill, that will really modify how people are able to take that medication.
Exactly. I don't have to go very far. My wife herself she doesn't like injections at all. And so anything that you can take it as orally, even for little babies, so injections are a terrible thing for a lot of things. And if you can have an alternative, of course, oral drugs are better. And I can tell you there are many, many, many extremely potent compounds which haven't made it to the clinics. It's because they're not water soluble. And there is no way of making if you try to modify it in a way that it loses its potency, and you can't make it water soluble. So it's really a chemistry problem. It's a chemist's nightmare, because on one point they put all the effort into developing that extremely potent compound, and then on the other hand, it either is not very soluble, it's not amenable for formulation or something like that, and then they have to give it in a different way. And most of the drugs which are given intravenously is because that's the only route. Given a chance, everybody would give it orally. Just to tell you a bit about this oral formulation, why it's important. So imagine, like any food that you eat, anything that you take it orally, it goes through through your body into the intestines, and then from the intestines it makes it through the bloodstream, and then it gets distributed all over the body. For the compounds which are not water soluble, they cannot do that. So that's why they are given directly into the bloodstream through intravenous injections. And the goal is to, at least Olexia Therapeutics is thinking of doing, is taking some of those potent compounds or the ones which are plagued by solubility, and if you can somehow make it better, more active by formulating it the way we do it, then you can bring a lot of those drugs which are crying in the shelves can be used.
Yeah. Yeah, interesting. Super duper interesting. Um, I think, yeah, I think it's so great, honestly. It's so important to be working on these things and to be thinking of like the best way to make it accessible for people. And I also think you were saying also more affordable.
Exactly. So one thing that comes is like like whenever you want to bring something, like even as a startup, you have to think of profitability, of whether is there a commercial potential. And I started out thinking that I would probably do it for the patients, and I realized that even to get to the patients, I have
You
to do
have,
all of
yeah.
this.
Yeah, you have to
Otherwise,
kind of
nobody.
do it for the money to do it for the patients. Because if you're not doing it, yeah,
It's
the
it's
system.
it's weird.
Yeah.
I'll tell you a story. I was at an investor meeting, and then one of these people told me, like, even if you make it cheap, do not tell us. If you tell us, then that that means you're putting the margin down. And I was like, well, okay, I understand, but uh,
Oh God, we must be in hell.
and
If
this
those.
was eye-opening for me. And I thought that like when you try to do how naive I am, because I was thinking at that time that no, we should make it affordable, and so the patients can have it, and if you make some bit of money out of it, it's fine. But the investor who has a business way of thinking already tells this is not the way to
Yeah.
go. And but then at some point you have to understand that you should not completely lose focus of why you're here. And that's why I try to keep that. I try to make it as affordable as
Yeah.
possible.
Yeah. You got to find that like Goldilocks zone, I guess, of how to how to make your product affordable, but also attractive enough that it's able to live and progress instead of also again sitting as an idea on the shelf. Could you tell me like what's happening? You said you're chatting to investors. Are you fundraising? What's happening?
I I am at the moment trying to build a team so that somebody can basically share the responsibilities as well. I'm fundraising at the moment. It's difficult for me because as we've discussed for the first 30 minutes, the profitability in antimicrobial space is not so much. And as a result, fundraising is difficult. So I have to rely on fundings which are given by the government, or some awards. I'm still working on an award money that I received when I developed this. Very little amount of money, but still, I am basically doing one job during the day, and after work, I'm trying to talk to people, trying to raise money, trying and also get some more results forward. And I'm benevolently helped by my old department. My boss still believes in the project. Although I've left, he's very generously given the time of a PhD student to take it forward in the academic way. But now it's the time that I'm really out there trying to raise money to build a team around it, and to not only stick to one product, but go to other drugs as well, trying to make it water soluble. And it doesn't need to be confined to antimicrobial space, because I believe that this technology can be used for other things as well, for other drugs, for cancer, for inflammation, for other. We have quite a few projects running in that direction in an academic setting, but I see the potential of the formulation, and it can be branched out to different things. And this is what I'm trying to do at the moment, to raise funds to bring the team together and take it forward.
Amazing. Yeah, it sounds like it could be the start of something really, really powerful. And yeah, maybe this is my call to the audience, which is that these things are team exercises. And so yeah, if you want to help out, if you want to get involved, in whatever shape or form that might be. We will link all the details in the podcast and, of course, on our social media as well. So please let this be your call to action. And if it's not your call to action, please let this be your absolute reprimanding to take your antibiotics for their full course. Yeah. Do you want to have any closing statements, any last sort of things that you want to tell us a little bit more about your company? Maybe reprimand everyone as well, if you'd like.
So yeah, I mean, so like if I were to close, is to make people aware that it's antimicrobial resistance is actually a silent pandemic. You know what COVID did, and you could see when everyone comes together, we can really bring down boundaries and make things work very fast. And development of new anti-infectives, be it antifungals, be it antiparasitics, or antibacterials, antivirals, all of this are important. And we have to find, even if there's not much money to be made in certain cases in the current model, we have to find an alternative model if that's the only way to go forward. If not, then I think academic research should be funded by also private entities, and also think of promoting young companies like Olexia Therapeutics, and so that they don't die before they were born. You know what I mean? So what started off as a dream we should be able to reach out to people and take it forward. Not just me. I'm speaking on behalf of many of my peers who have met at several conferences, who are trying to spin out a company in the anti-infective space and are finding it very difficult to survive. They almost always have to rely on another job to even take it forward. It's the passion that drives us on, but the passion needs refueling every now and then, and in whatever form that comes, you're more than welcome. And thank you so much, Ella, for hosting me. And it was a great pleasure.
Of course. That was, really, really rousing. I completely agree that there need to be shifts to the system. And I think, I mean, DeSci for me is it's young and it's unformed, but I like that it's a bunch of people sort of coming together and trying to troubleshoot these systems and develop new systems in whatever way we can. And also how much it prioritizes the impact of community. I mean, as you're saying, your old professor who's allowed you to, have a PhD student that's still working on it. That's really just good people looking after other good people. And hopefully, it's enough.
Yeah, I mean, we need a little more than that, but I can't complain at the moment.
Yes, very fair.
I can't complain at the moment. You've very generously given me a lot of time to talk about my research and the stuff that I'm trying to do. And with this kind of platforms, I hope more people get to know about it. And as I said, in whatever way any kind of help comes, we'll be very happy to accept it.
Okay, everyone, thank you so much for listening. All the details will be linked in the podcast, and we'll see you soon. Thanks, everyone.